In the past, we have used implicit differentiation, among other things, to try and find the slopes of curves which are not functions. Well, we're going to have a look now at how we can achieve the same purpose, but by using partial derivatives. And of course, the connection between partial derivatives, or generally between functions of two variables, and implicit differentiation is the idea of a level curve. So let's assume we have a level curve written down as an equation, where on the left hand side there is some combination of x and y, which we can think of as a function of x and y, and 0 on the right hand side. In this way, we are assuming also that y is an implicit function of x. By the way, that 0 on the right hand side is not really a special case, because of course if we have some relationship between x and y which has non-zero terms both on the left and on the right, we can always move everything to the left and make the right hand side equal to 0. So we can always get ourselves into this kind of situation. Well, if this is the case, then the left hand side can actually be seen as a function of x only. All we have to do is we have to substitute instead of y, or think of y as a function of x, and so we have that our function f is a function of x in the first input directly, and of x in the second input indirectly through y. Okay? So if that is the case, then we may want to compute the derivative of this function as a function of x only. So according to the definition, this is going to be the limit as h approaches 0 of f of x plus h and y of x plus h minus f of x and y of x, all over h. Now, you may want to pause here and think about where that comes from. Of course, that comes from the usual limit definition of a function, of a derivative. But we have a situation where remember we have to change x to x plus h in the first term of the numerator in two places. Okay? Now we're going to play with this formula and see where we can get. Now we're going to use some standard methods, but we're also have to check at some point lots of details. But you know, don't faint. Don't worry about it. We're not really going to check the details. I'm just going to tell you where certain details need to be checked, but we're not going to check them. Okay? So instead we're going to focus just on the usual techniques. For instance, one thing I can do, and so I'm going to give you just a sketch of the process. One thing we can do is we can add and subtract something. You may remember this technique from the proof of the product rule. So what I'm doing is I'm rewriting that same fraction, leaving some space in between. Space in between for what? Well, it turns out that this is what is going to work. So we're going to add and subtract f of x plus h and y of x only. And again, you may want to compare this to what we did with the product rule. It's pretty much the same thing. And if you remember that proof, you may remember that the next step is that of splitting that fraction. So we're going to split that into the limit of the fraction obtained by using the first two terms in the numerator, plus the limit of the fraction obtained by using the last two terms. Okay. Now, the last limit, the one on the right hand side, is quite easy. If you think about it, what we have is we have f of x plus h and y minus f of x and y. So we're making f be a function of x only in the first input, keeping the second one fixed. Well, if you remember, that's what we defined as the partial derivative of f with respect to x. Now, here is one place where I'm waffling a bit. There are in fact some technical issues that need to be checked out, because remember, we're assuming that y is actually changing with x, so we'll have to be a little bit careful there. But again, your intuition at this point works quite well. So that last limit is just del f by del x, and what we need now is we need to take care of the first limit. Now we're going to use another technique that we've used before, multiply and divide, sort of rationalizing. So what I'm going to do is I'm going to multiply and divide this fraction on the left hand side, not by the conjugate of the numerator, that wouldn't work, by this expression, y of x plus h minus y of x divided by the same thing. Alright, so what is that going to do? Well, first of all, the way it is right now is not going to do much, so what we're going to do is we're going to switch the two denominators. Now you can tell that the second fraction now is starting to look familiar. Well, the limit is h approaches 0 of y of x plus h minus y of x over h. Well, remember, y is a function of x, right? And that is exactly what will give us the derivative. The details come in now when we're going to try to figure out what that first fraction looks like. Well, it turns out that the first fraction, and again, this is where a lot of the technical details will have to be worked out, but it turns out that the first fraction is in fact the partial derivative of f with respect to y. You can convince yourself of that by noticing that in that formula, x is the first input is constant, right? It's x plus h in the first one, x plus h in the second, so we're assuming that x is constant, and what is changing is the y, which is moving from y of x to y of x plus h. Now we don't quite have just the h in there, but again, there are some details that need to be checked out, but it works out. And so the first that first fraction turns out to be the partial derivative of f with respect to y, and the second one turns out, as I mentioned, to be dy dx, and of course the last one was del f del x. Okay, now let's try and recap here. What are we doing? Where were we at? Remember, we were trying to compute the derivative of our function on the left hand side, thought of as a function of x only, right? So what we figured out is that the derivative of a function of two variables with respect to one of them is going to be equal to the derivative, the partial derivative of that function with respect to the other one, times the derivative of that second variable with respect to the first, plus the partial derivative of the function excuse me, with respect to the first one. So, by the way, this is a formula that you can use in other situations as well. Whenever you have a function of two variables and you're assuming that one of them is a function of the other, and so you want to compute just the derivative, not the partial derivative, but the actual derivative of the whole thing with respect to the real independent variable, you can use that formula. But what does that tell us in our situation? Remember, we started by saying, well, we have this implicit relation between x and y, which is described by that equation. Okay, if I take the derivative of that equation, I end up, the derivative of the left-hand side is going to be df by dx, and the derivative of the other side is still going to be 0 because it was 0 to begin with. Well, but now I know what df dx is, right? And so I can substitute, instead of df dx, I can substitute del f del y times dy dx plus del f del x, which is what we just found. And it turns out that that one is going to be equal to 0 because the right-hand side was 0. Well, look at what we can do now. We can solve for dy dx. And that's going to be equal by moving the del f del x to the other side, and then dividing by del f del y is going to be equal to simply minus the ratio of the partial derivative of the function with respect to x divided by the partial derivative of the function with respect to y. And what's dy dx? But of course it's the slope, right? So this formula allows us to compute the slope of this implicitly defined relationship between x and y by using partial derivatives. Now, I've gone through a lot of details, technical stuff and so on, so you may want to rewind and look at it all over again. But basically the long and the short of it is that we have developed an alternative method to implicit differentiation in order to find the slope or the rate of change of a curve, say, that describes an implicit relation between x and y. So if you don't like implicit differentiation and you prefer partial derivatives, then you can use this formula. I will leave it up to you to figure out which one you want to use. In any one situation, you may want to use one or the other, except that sometimes I may ask you to use one of the two methods and not the other.